All right, so second recording. Probably need to stay more in the camera. Okay, so I did some updates to Blackboard. For one, there's the first 150 pages of the textbook. And then if you go to the syllabus, I linked the YouTube sub-channel. I have several sub-channels. And this is the recording of, I think we missed 3-4 minutes at the end. Probably no more space on my cell phone. Okay, so I don't know how many of you tried it. I can see how many viewers. 3 subscribers, 3 views, 3 subscribers. Okay. So yeah, well, the good thing is you can play them fast forward. That is 25% faster. You can replay things that you consider require additional listening to. So let's see, is the book? Yeah, the book is still here. Sometimes they delete them once you go out of session. Okay, so we're still at chapter 1, and the book does some reviews of the statics. I said that this class relies substantially on what you learn from statics, including area properties, center of masses, centroids, area moments of inertia, something that you did in statics, and we're going to maybe wasn't clear when you did those. Center of masses maybe, or for sure, but area moments of inertia might not have been very clear then. It will be, once we go, will become clear why that's studied. And that is when we'll discuss bending. All right. So I think we covered everything. The book has, this one, 6th edition, has on page 496 is an insert of color pictures. It has this one that's on the screen. Would have been nice to also have the photoelasticity exam that was before it. This one, where is it? This one, it's in color in the 7th edition. Probably could could Google. I'm sure Google is a great tool. So Google and say search. Thank you. Is this no? Okay. So photoelasticity images, and let's see which one would be relevant. Yeah, maybe here. Some open in a new tab. Okay, so it shows what, a specimen that is subject to tension, very likely, and you can see as the notch, the neck here is the same, but the fillet rate, the transition between the two sections, is increasingly abrupt. And what this causes is localized increases of the stress, tensile stress. Again, this is subject to tension. And well, one thing you have, so maybe here it looks even, and so an average stress would be a color like this one maybe, but locally you can have, and as we give here, locally you can have higher stresses with areas of lower stress. The higher than average or nominal stress cause local yielding of the material, and that is particularly when you have tensile loading and fluctuating loading. that can be spots where crack develop and you can have fatigue failure. I think I mentioned last time the case of an airplane that lost an engine in flight and was because of fatigue bolt that supported the engine, attached the engine to the wing. Okay, so in strain gauges, either then numerically running experiments for before you commit to a part. And there's the book doesn't mention it. There are packages that can allow a what is called structural optimization. So you define it as a parametric part and ranges that can change, say this dimension and this one, and maybe an angle until for a given loading you get the stresses minimum possible. I was looking for an example on, we couldn't find it, but I knew of a study where the piston pin of engines currently is just cylinder and has some more generous tapers at the end. That the piston pin, you want to be lighter weight because it moves with the piston, right? And the lighter the piston, the entire moving masses, the lighter the better for balancing or shaking reasons. Anyway, so after this type of what's called design optimization, and there again, it's done in software, it got to a shape that was maybe not as easy or almost impossible or too costly to do trial and error. So this is where engineering is going. When it comes to design, you want to maximize performance, reduce mass, reduce cost. Even for at that shape, the piston pin would have been more expensive to begin with, but with other benefits. I know of a case. I have a friend that does research work for Toyota in Michigan, Ann Arbor, and they changed from a turn machine connector where the oil filter goes, there's that nipple there. They made it instead of hydroform tubing, and that saved pennies. But when you fabricate hundreds of thousands, millions of engines of that same type, pennies add up to tens of hundreds of thousands. Anyway, but the difference was that when he worked on that, what's the resistance to fluid flow as the oil passes that modified nipple over the original design. Okay, so some warm up on this on strengths and materials. I said it's important. You can do a leaving. Of course, you need to add to it. You haven't taken manufacturing processes, but you're reading the book. It's something that you have in mind. Can this part be machined efficiently and economically? If it's too expensive, even if it's the best one, you need to go for suboptimum just because of maybe the story was the optimized piston pin was difficult to machine, and they they still put on engines or the older design. Anyway, so let's try some problems. Here, all we need to just so evaluate the loads, and there will be tensile compressive loads or shear, direct shear, and calculate the stress. That's what we can do with the knowledge up to chapter 1. As we move forward, learn about design properties of material, and I hinted already the yield strengths when there's a permanent deformation, and there will be more to it. I need to discuss that. It used to be a lab that went to this class. Now all labs are in one class that you take separate engineering lab. I don't know if you civil engineers take it, the engineering lab, but has a tensile experiment. I think they do for sure. Hardness test experiment. They might do the impact test. And these were done in material science historically. For this class, we're doing some experiments with strain gauges. And I think they do some of those. So yeah, but you're going to take them as it's called solid mechanics lab. Maybe you already registered for solid mechanics lab. for fall. Okay, so like I said, if you know the limit property of the material for a component, so you have this, it appears to be a shelf, and this could be a cable. Why can be a cable? You know, you have the way, it's quite a bit of a load on the shelf here. It's almost like parking a car there, but the width is substantial. So yeah, it might be a shelf on some Amazon warehouse. So, and I said this could be replaced with a cable because it's in tension. This also, we know it's from statics. Do you remember its name? The two-force member rings a bell. So this is a two-force member. However, this is not. So it's a two-force member wherein it's subject to just tension. And when you see pins at the end and no force that is other than in line with the axis of the beam, okay, that's no longer two-force member. So the shelf itself is not a two-force member because we have a force, external force is applied perpendicular or at an angle, okay, at an angle. We can make this two-force member if we take this force and you pull it this way, okay? So if you make the force horizontal in line with the pins, then this too becomes a two-force member. Okay, so the question is, what is the stress in the support rods? Sometimes you have a duplicate of supporting, so you need to pay attention. It means that in a model showing just one rod, you take only half of this force, or you calculate the tension, but then you divide it by 2. Does it make sense? So they share evenly the effect of this load here. So yeah, what we need to calculate is the tension in the two support rods, and we can calculate the stress if the cross section is given. So the diameter, each rod diameter is 12 millimeters. Okay, that's ½ inch, a little bit under ½ inch. So, so let's see. One thing I could do, so F print screen and go to paint and paste and take just this this rectangular selection, copy, undo, paste, and let me put it to where we can look at it, and let's solve this problem. So again, there are two rods. So we're going to, in the model that includes just one rod, we're going to take half of the load, okay, for that reason. And we need to do a free body diagram that is helpful to calculate the tension in the rod, okay? So, I mean, we can do a free body diagram for each individual members. So we have the lower, the shelf that is, and here we have a pin joint, so there will be a, and we're assuming them to be positive. So let's call this A, B, and C. So I have R, A vertical, R, A horizontal. Again, the support rod BC being the two-force member, I know that the pin at B, I'll have a force, and I can tell its direction already. So the force, again, I'm trying to get to where is I'm copying the angle. So this is the force tension in the rod BC, okay? And then in addition, we have the weight, and again, the forces are in sliding vectors, so I can show it anywhere above, below, maybe tail at with a payload, probably center mass will be about. Anyway, so this is we said half of it, so 1840 divided by 12 kilograms. This is 620 kilograms. The load, hey, I need to multiply by what? Times 9.81, times G, right? 9.81, so 9.81 times G, and this will make 4 newtons. Okay, so this is a metric problem. Oh, by the way, in case you show to camera, so if you have ever handled a plastic T-wrench, there you have. Or you have it. So 9.81 times 620, this is, yes, you're right. Thank you. Thanks for paying attention. So 9.81 times 920, this is 9,025.2 newtons, okay? And again, points are A and B here. And then I can do a free body diagram. Let me make it shorter, the FBC. Okay, and I can show the link. I need to move it off its original location. Okay, and I'm showing it will be the same FBC. And then here I have FBC. Again, neglecting the weight of the support rod. Our analysis will go, because it's where the input force is given, we'll go with rod or the shell itself. Do you follow? Okay, so this is the unknown. Once we know this, we can calculate the stress, tensile stress in the link BC. And this is going to be FBC divided by diameter of rod BC. So it'll be FBC pi, and there's a diameter squared over 4. Okay, so we have this already, it's 12 millimeters. We need to calculate the force. So how do we get the force, FBC? Any takes? Okay, so the recommended way of doing it is to use the moment equation and then switch or use the force equilibrium equation to verify calculations, okay? So we're going to sum moments about point A. It eliminates these two as unknowns. By the way, we have 3 unknowns here. So there's 1, 2, and the third one. Don't forget, we have this angle. So this is 30 degrees. So the knowledge about the angle, then I could put the horizontal vertical components at B, but then I know the angle between them. Here I don't know the angles between the horizontal vertical components, okay? So I have 3 unknowns, and I can write 3 equilibrium equation for the shelf, and with that I can solve for the 3 unknowns, all right? But really I'm interested in just this one. So you sum moments, we don't care about these 2. We can calculate them if needed. Say, if we want to calculate, maybe we'll do this. So let's assume this to be, 0.5, well, I said inches. So let's assume it's 10 inches diameter. And calculate, I'm just improvising. This is jazz sometimes. It can turn it. So we're going to calculate the shear stress upon a pin here, but we need to decide what kind of, is it double shear or single shear? So over the text of the problem, you can make a note. We're going to, after finishing what is required, to calculate the shear stress on the pin. All right? Okay, so I said some moments about point A, and we have equilibrium. And I tend to take, my choice, positive counterclockwise. So, it pivots about point A, and as I move to the right, I see the moment. So it turns into, maybe copy some information from. So this is 600 millimeters, and this will be also 600 millimeters. Okay, so I say a negative, positive, I said is counterclockwise, negative, 9025.2 times the arm of the force, 600. And then I have the moment caused by FBC, which is the unknown. And that's going to cause the horizontal component is just pushing through the pin. It will be the vertical component of FBC that's causing the moment. So there are 2 ways to calculate the moment, if you remember from statics. You either calculate, we can do both. So either calculate the arm of the moment. Okay, so I can say FBC times this distance, let's call this D. So AD. All right, so I could go that way. So plus FBC, this is not a preferred way in my judgment, times AD equals 0, and it's causing a positive moment. I assume positive counterclockwise, okay. Or I can say negative 9025.2 times 600 plus will be FBC, and be careful, don't show both the original force and its components. So I'm using different color and dashed. So a moment causing force would be this vertical one, right? Times y, because I have this arm of the vertical component readily available. So it'll be FBC times what? This is 30 degrees. So it'll be times what? It opposes the angle, so it's, this is here, and it's sine of 30 degrees times distance AB, okay, equals 0. We can calculate AD from geometry. We have a right angle triangle where we know an angle. So AD is going to be what? AD is going to be AB times sine of 30 degrees. Okay, and we can solve the problem this way. So AB, that was 1200. So 1200 times 30 degrees is half, 0.5, 30 sine equals, so this is 600 millimeters. Don't forget units. So 600 millimeters. And you can solve for FBC here. It's going to be, move this to the side, so 9025.2 times 600 over 600. So this is 9025.2. I think I'm out of camera. All right, newtons. But the same we'll get if we solve this one. Actually, it stands to reason, because if we carry this with us here, we get the same equations. The sign coming from different analysis, different geometry. Okay, so FBC from this other equation is going to be, becomes positive 9025.2 times 600 over sine of 30 degrees times AB, and that was 1200, okay? So it's 9025.2 newtons. Okay, so we have a force. And with this, or the force that we're looking for, rather, then we can calculate the tensile stress, sigma, in the rod BC. And you know what? I think have we divided this by 2? Yes, we're correct. Double check. Oftentimes, this trivial step is overlooked, like usually happens in practice. The simple things get, a $2 ball causes most hassle by failing. Anyway, so we've got a force, we can calculate the stress. So it will be 9025.2 over pi 12 squared over 4. Okay. Remember this. Maybe you've been told about this. So if you were in metric, if you work everything millimeters and then everything newtons, you'll get the stresses. And so you have Newton millimeter for moments, areas in millimeters squared, moments of inertia in millimeter 3 or 4, depending on what kind of moment of inertia, stresses in megapascals. The equation will be balanced. Okay, you don't need to go through meters. Does it make sense? So remember, all millimeters, all newtons, and all stress is megapascal. So this will be megapascal. And let's see what the answer is. So I have 9025.2 over pi over 12 squared times 4. And this is 79.8 megapascals. Is it clear so far? So really, this was statics. Finding BC was statics. What you learned yesterday was this additional step to calculate tensile stress. You have a question?
It's written in the problem.
It's in the text of the problem. So if you go to, the shelf-based design holder crates. So problem is 141. Let me just say, so problem, approach the problem from the right hand and state the essential. So problem is 141, and this one, the diameter was given as 12 millimeters. Okay, in the text of the problem. Thanks for the question. Other questions? Yeah, 12 millimeters. Okay, so again, this was all statics. This was the new part. You take the area divided by, again, this is direct tension. Assume even the two-force member, recognizing a two-force member. So we've got a problem solved. If we know the material of the rod and we know its tensile properties, then we can declare the design safe. Okay, so I can relate to yield strength. I can relate to ultimate strength. This one here, if it yields once, no hard feelings. Remember, the airplane was the wings that ended up a foot higher, and they continue to fly it. But if the load is applied repeatedly, then you need to start thinking more. What possibility of failures are? What the design recommend? We haven't discussed design factor or factor of safety. That will be. I'm anticipating. So design factor N would be the ratio here for, let's relate it to yield strength over design stress sigma D. So let's call this design stress. And you want this number to be, depending on the application. If it's a building-like structure, code experience tells us that a number that is 1.6, 1.7 would be okay. Mechanical engineers work with numbers like 2, 2.5. Why? Again, I'm anticipating is a chapter 2 subject. So why have design factors to account for uncertainties in load? This may get overloaded for, accidentally somebody may climb on top of the crate and increase this over the anticipated value. Aging, you have corrosion. You need to be careful if it's corrosion. Corrosion weakens. It could be, like I say, oftentimes it's elsewhere that you focus your attention that failure occur. The clevises at the end. So you're putting your signature on the drawing. And you're responsible if it fails elsewhere that you anticipated. You're responsible. You need to cross your fingers and nobody gets hurt and learn from mistakes. But again, there's code and recommendation on what to choose here. It could be the reference property of the material could be instead ultimate strength. Okay, so we pass the yield point and we the tensile specimen, we'll see you stretch it until it fails, and that's the maximum stress that it can hold, although following some elongation. And that might not be acceptable because you can get the shelf going off horizontal position, and that might not be acceptable to begin with. Okay, so and then we said, so this was it, problem solved. Let's go to the pin here, and okay, so we have a pin, and appears to be, if you look at the 3D view in the book, I can go to the book. So let's look at the and what kind of shear do we have at the pin? So looks like there's a long pin that goes from this bracket all the way to this other end, or maybe it's just I don't know. They don't say this how long it is. Having a hole that is this long might be an issue. So this is not the best design. I would comment. It might just be a pin that was mounted on a bracket and bolted. In any case, this is single shear here, right? and it's single shear here. If we work with the full pin, say it's in double shear, we need to what? We need to take the, and don't forget, this is just for one side. We need to double these going back to the full load, and then we divide it by 2 again. So we work with what we have and assume the pin in single shear. Does it make sense? Again, we analyze just 1/2. And if we, 1/2 in one pin, the other half, the other pin, or could be one through pin, less likely during this long haul is, you'll receive phone calls back. Are you sure you want this long haul? Okay, we can do it, but pay us thousands. Anyway, so let's calculate the shear stress. So tau at the pin, we can call it pin, or we can call it design stress, and that's going to be the what? It's going to be the resultant reaction force at A divided by area of the pin, pi diameter of the pin squared over 4. So what does it go here? The vector sum of these two, okay? So it's going to be square root of RA horizontal square plus RA vertical square. Everybody agrees? I'm seeing puzzle faces. So we're resolved. Let me turn or go back to paint. So first of all, again, don't dismiss this. You say, okay, it's not in the book. He's making it up. You will forget about it. No. You won't see just this. Life of an engineer is not a textbook, or problems that engineers solve are not textbook problems. Sometimes you have to formulate the problem, okay? And even go over what the management says, because you know your problem better. I work as a design engineer, and I can tell you stories where management comes in, and because they get better salaries, they think they know more, or they know a lot. They don't. They don't. They haven't slept on your problem. You know better. Have the guts and tell them. I'm sorry. I think I have a different opinion. Let me explain. Okay? I cannot emphasize it that much. It was on, I don't know if you know Quora Digest. So somebody is asking, is it true that engineers apply in their profession only 10% what they learn in college? And yeah, very likely. So you may go a different route. You can maybe go in sales, or you want to do thermal fluids, or very little of this. Use code and internal rules of the company, whatever. But there are things, on the soft side that you should remember. One, the example that I gave, have the professional courage to tell a mistake. Yes.
I had a question about the numbers.
You interrupted me. I was about to finish an idea, but you shouldn't learn to go along with deceit, with cheating and being wasteful, for sure. Yes, I'm listening to your question.
When you wrote it's like a Z, you said tau. Just wondering.
This one here?
Yeah, it's like stress.
This is the shear stress, and this is tau. This is my tau. This is my tau. I do this and this and this. My T looks like this one. They are not the same. Let me show more taus. T's, T's, T's. T, T, T. Rosetta Stone. Okay, it looks like a pie to you? Or the pie? Okay, pi. So this is pi. What about that? Okay. On camera was not visible. Okay, so we have the next part, the continued problem, calculate the shear stress in the pin. We need to calculate somebody I should have just say, let's clarify where is this coming from. Anybody understand where is this coming from? Well, maybe some don't. So we resolved into the horizontal vertical component for convenience. We can assume a vector and an unknown angle, the resultant and the angle. Let me make this a bit more general. Let me make one, and sure it is. Or you never know until you put the numbers on. So there will be the resultant R at A okay, which is the vector sum of these two vectors, which are orthogonal, and that's why this, okay? And you can, or preferably you work with the two orthogonal components, could have chosen an XY frame, or you can assume a resultant and then an unknown angle, whatever choice for an angle. So yeah, I can go with RA and an angle here that are the unknowns. But you have to go through the steps of saying maybe, you know, RA sine of alpha to get you this, and okay, so I'm overemphasizing. This is statics. You've seen this before for sure. Anyway, so we need to calculate the two components. We exhausted, maybe not, the moment equation. We can apply moment equation about B. I prefer moment equation for calculations, and again use sum of forces for to verify results. So I can, in order to take care of the resultant at A, I can sum moments about point B. You will see us doing this over and over. Likewise, counterclockwise is positive. Sum of moment about point B equals 0. Sum of forces might be the tempting one because it's easier. Okay, so what do I write? I have FB does not carry any moment because of the arm is 0. So I'm saying RAV, and that's a negative. So negative RAV. And then I have negative positive times what? I'm sorry. Times the full length, 1200 millimeters. And then I have the positive moment, the counterclockwise direction of this force, 9025.2. So 9025.2 times its arm is 600 millimeters. By the way, here, nothing to do with the millimeter megapascals. You can use meters, not to carry zeros with you, just because it's different business here. We do statics. When we calculate stresses, like I said, millimeter, megapascals, newtons, equations are balanced. Okay, so this is the moment equation, and it's going to give me the vertical component. So the vertical of the reaction at A. So RAV is going to be 9025.2 times 600 over 1200. Okay, so this is half of 6 divided by 12. That's 2 or 1 over 2. So 9025.2 over 2. This is 4,500.6 newtons. Okay, so we have one component. Now for the horizontal component, I cannot, there's no moment where, can I write a moment equation? No, unless I choose a point outside of the beam. So for the horizontal component, I'm going to just sum forces in the x direction. So sum forces in the x direction have equilibrium, again, for the shelf, and we assume positive to be to the right. Okay, so what do we have? We have the unknown, and again, positive to the right. So I have RAH, and then I have nothing here, and I have the horizontal projection of this force, so FBC, negative FBC, times cosine of 30 degrees equals 0. We've got FBC calculated earlier, 9025.2. So we can solve for RAH, and that's going to be 9025.2 times 30 cosine equals, this is 7816.1 newtons. Okay, so we have the two. We can implement this equation. Was it clear what I've done? So again, this is statics, all statics. Don't forget FE quiz on Thursday. So tau at the pin is going to be square root of the horizontal component, just got it, 7817.1 16.1 I say square plus the vertical 4512.6 squared divided by pi, and now we assume that 10 inch, or rather 10, I said 10 inches, we don't mix inches with it, so 10 millimeters, let's see if 10 millimeters is a decent value. So 10 squared over 4. Okay, so I have this last one and I square it, plus 4512.6 squared equals square root divided by pi times 4 divided by 10 squared is 100. So I have 114.9 megapascals. Okay? And this is a pretty serious shear stress. So how do we relate? We calculate design factor. Again, I'm anticipating this is all in the next chapter. So we can calculate here design factor. And again, is it fluctuating load, apply or remove, apply or remove? You know, very likely in the life of the shelf, you put crates and you take them off. Unless it's a shelf for a museum. You know, when you, in every 10 years they come in and check, are they still there, or somebody sold them on eBay, the dinosaur bones. So we calculate design stress for the pin, or at the design factor for the pin, and here we relate to, let's say, yield strength and shear over tau pin, and I said we call this design factor, not design factor, shear stress. Okay, how do we get this one? Is not readily available, so you need to make an approximation, and it's usually it's taken as half of the yield strength in tension. The tensile stress is rather easy to perform. All you need is just a specimen, cut to size, you know, same material but to size, and size matter really. And you put a tensile machine. You do this for multiple samples. And you know, it's available from the supplier. The shear properties are not that the shear test is difficult to perform. When it's done, you do it sheared through twisting. So what they do, they fabricate a fabricated tubular piece with an area that is very thin, and they twist it and they record the angle, same as they do with the tensile specimen. But here you have torque and angular displacement, here you have force and linear displacement. This is easy to perform, and the specimen is easier to fabricate. That for the torsion test, you need the tubing with the neck, and so very unlikely I won't find this information readily available, like direct test of it. It's calculated rather approximately, and you usually take 0.5 times the yield strength in tension. So if you think 0.5, it means that we are, you know, assuming the same material, it might not be the case, that are, you know, worse at the pin than we were at the rod. Does it make sense? So here, in order to get to design factor, I need the yield strength of the material of, what was it, like 160 megapascals. That's pretty decent, you know, good quality steel, and expensive. But if you want to use the same material for the pin at this diameter, which I assumed, then you'd need a very high strength steel, and that is even more expensive, probably hard, difficult to work with. So what do you need to do? Go back to the pin, increase its size. It might need to be, well, maybe a full 20 millimeter diameter. And this is what design engineers do. The one approach is to just do repeated analysis. You pick something based on your experience, your flair. You run the numbers. It says it's not okay. I need to go back and make changes. at the pin. Or maybe you just rate the shell for less load. Check with the customer. Okay, do they really need to put here like an automobile? Anyway, so was it clear? Any questions? Yes.
So we have to do that bottom ratio one in order to see that's a good number?
Okay, so I anticipate we're going to discuss design factors. Okay, so in order to build a little bit more of what you've learned so far, I went to introduce the design factor because we did a lot of statics, and then what? We took a force and divided with an area, and we looked at the number. So what do you do with that number? Well, go to the next problem. In reality, and you will see, before the end of this week, we're going to do this kind of things. Calculate stresses and evaluate design factors, okay? And design factor tells you how far off you are from failure. What is failure? Permanent deformation or fracture, okay? So it's what we did. We went a little bit further and looked at some numbers. What is, have we assumed here any? No, I just stated this equation. But we can assume some material here. We go to the back of the book. If you have the book, there's appendices that list tensile properties of various steel materials. So I'm on, I could do it from the textbook and project it. So let me lower the screen. We lower the screen and we can go to, the text. And at the end, there are some appendices. Actually, where's the old tools? Oh, the table of contents is here. So you have appendix, and you have properties of areas. Okay, so other than the more classical like area and where the center of mass is, if it's symmetric, then you know where it is. But for parabolic shapes, there's some formula here given, and then you see. Let's see, you have prefer basic size. We discussed about that. You go with 1 inch, inch and a quarter, inch and a half, inch and 3/4. Remember, not just or if you're to go in between, pick numbers that are easy to remember, easy to work with, and then screw threads, and then probably standard wood bores is working with wood. And structural steels, and then it says typical properties of carbon and alloy steel. That's appendix 10. Doesn't say what page. So we need to go down the table. So this is area properties, channel, YW sections, I-beams, box tubings, aluminum. I know aluminum because it has sharp corners here as an off fillet, and there are aluminum. Does it say aluminum? And then typical property is carbon and alloy steels. So carbon steel is for machine parts. For structure, you use what is called structural steel. Okay, because that's the type of steel that you can find tubing, structural tubing, and I-beams and channels and hollow structural steels available. This comes as bars that you can turn and cut and weld on them. So let's just look at these numbers here. You had material science. I know you had material science, a prerequisite for this class. So in material science, you learn about various type of ferrous alloys. Have you? Ferrous alloys. So that is steels with alloying element. These numbers here are for plain carbon steel. How do I know? Because there's a 0 on the second digit. The last two tells us the carbon content. So this would be the low carbon steel. This is the medium carbon steel. This is high carbon steel. These weld nicely, but they are softer grades, malleable. These can be heat treated. You can quench and temper them not to crack and use quenching. increases your hardness, but they also become brittle. And you want to do a little bit of the hardness, but you get more toughness to them. And these are the tool steels, high carbon steel. The files, chisels are made of this steel. This is hard and brittle. And then you have alloy steel. These are medium carbon steel that is, so I'm looking at like, it says 20 points of steel or 0.2%, 0.2% carbon, 0.4% carbon, 0.8% carbon. All right. Now these start having numbers on the second digit. So they're alloying elements, and those could be, chromium, manganese, other type of alloying elements. And why is that? Because improve hardenability. What does that mean? You can achieve the same hardness like for the plain carbon steel, but with less severe cooling. So instead of dropping it in water, you let it can hardens in in air. And by cooling them slower, there's less likely to warp. You remember from material science, so hardening comes with phase change, and phase change is slight volume change, and because of them they can warp, particularly thin areas. So there's geometry change after heat treatment. You need to do one final machining, grinding the areas that you need to control the say you have a shaft that there's bearing that need to go on certain areas. After heat treatment, that diameter, it's slightly different than before, usually bigger. And you might not be able to run the bearing. So you need to put it on a between sander and grinding wheel, and not the one that you hold to grind the knife. They're machined to do precision cylindrical grinding. I don't know, don't look elsewhere. So an engineer has to be aware of all these aspects. I said the public does not know what it goes. So when you design a product, you need to have all these in mind. You juggle with a number of balls at a time. Its cost, its manufacturability, availability, this kind of things. Anyway, so these are carbon steel, and you can see here the condition. So it's annealed. This is a treatment. It's you heat it red hot, and then you will slowly cool it, and it's soft and ductile. Hot rolled, larger sections become hot rolled. Cold drawn. Usually don't expect a bar that is half a foot diameter to be cold drawn. Only the smaller sizes. Those would be harder. You can see the ultimate strength for the cold drawn. It's higher. And then these last column, it tells you what is called percent elongation. So this is an indication of its ductility. If this number approaches 5% elongation, that's a material that it's less ductile. You cannot bend it. You bend it just a little bit and pops. Okay, this is very ductile, annealed. Okay, and then you have water quench and tempered, oil quench and tempered. And you can see was heat treated. I mean, this is heat treatment too, but the hardness went up. It's the same material, but the condition matters. The ultimate strength, it went up like what, 60, 70% because you did heat treatment to it. These are not quenched in water, but rather in oil. There are other quenching media like malted salts and air. But again, based on the condition, you get different mechanical properties. You don't see here any, so this is the ultimate strength, which is always a number bigger than the yield strength. Okay, yield is where the first permanent deformation in shoes, like 0.2% permanent deformation. You take the load off. It's not as long the specimen as was before. If I bend something, it's slightly bent. Okay, only slightly. Versus ultimate, where I can, if I'm doing bending, all these for tensile. So I push until it breaks into two pieces. Okay. All right. So, and more information. Don't forget the footnote and explain what oil quench, water quench, and tempered. You look at the other. There are ways of rotating the view. Rotate view. So look at this other one. These are stainless steels. There are various types of stainless steels. By the way, SAE, Society of Automotive Engineers, now it's in charge of designation for various steel material. They're in need of various steel grades to satisfy their strength requirement and also cost. There's a type of high strength, low alloy steels. Alloying elements make the steel expensive. Nickel is one expensive material, if you wonder. Not as expensive as, or chromium is less expensive. Okay, so we have the stainless, and some of them are the, let's see, these are the austenitic are called, and the magnet doesn't stick to them. Cutlery, it's a different type of stainless, and it's magnetic, but the austenitic is non-magnetic. And then we have copper and bronzes, and copper, that is, bronzes are alloys of copper, and other than tin, brasses are copper and tin. You have zinc materials, and then usually used for in cast forms, like die cast, little toys, toy cars you play when you were a kid. They look heavy. There's metal die cast, and it's easy, low melting point. Used quite a bit to for intricate small size parts. Nickel-based alloys, and then we have let's see, I need to rotate backwards or back. So we have structural steels. Okay, so what we looked at, angle iron, box tubings, I-beams, they will be available in this. So it says available in shapes, plates, and bars. Okay, you can find in pipes. This is high strength, low alloy, corrosion resistance plate. Again, it might, so you need to check and make sure that a certain grade steel material is available, readily available, certain shades that you need. So if you plan on using an I-beam that is made of stainless, that might be a special order, and you're not being able to find it, or if you do, they'll be very expensive, unless you build something in large volume, and it's worth, making a special order if it makes sense, okay? But for general construction, just focus on what's available in the grades that is available. Again, these are structural steels. A36. 36 is the yield strength, all right? And cast iron. Okay, cast iron. Do you know what cast iron is? You had material science, right? What's cast iron?
Cast into a mold.
Just because I said cast iron, well, it's iron. Okay, it's iron, and has high carbon content. It's over 1.5, 1.2, I think, and percent going towards 2% carbon content. And there's too much carbon, and it as you cool it, precipitates as graphite flakes. Although it can be trapped into the crystal structure, graphite flakes can be controlled with addition like silicon. You add silicon to the iron, and you get various types of. So you see here like gray iron. This is the ordinary, the most ordinary of the irons, low mechanical properties. You don't see here yield strength. Iron is, for the most part, there's some there where it says ductile iron, but iron is brittle, okay, and has different properties, and you can see compression and tension, all right? This might be for shear. So it's not even listed the tensile properties of gray iron. So it has anisotropic behavior because of the graphite that precipitate out of iron. If you have ever seen like a broken old bathtub, well, iron, you can find the ductile grade or malleable like hammers. They're not very expensive one. The ordinary shop hammers, they're iron versus those made of steel. They cast well. The thing is, they melt a lower point than carbon steel, and it's fluid, casts very well. You can get intricate parts out of iron, okay? But the graphite to them, depending on the way it's formed, the way it's precipitates, the graphite and the percentage of carbon dictates or conditions the mechanical properties. Okay, but again, remember, you don't have yield strength listed for irons, and the tensile compressive ultimate strengths differ because iron is anisotropic. It's stronger in compression. And then we have aluminums, woods, plastics, and this is a table that you want to bookmark. So A17, this is a summary of what? Essentially, you look at these numbers and they are design factors. We call them N, but here it shows just a ratio. So design stress, yield strength divided by 2, this corresponds to a design factor of 2 with reference to yield strength. This is a design factor of 8 with reference to ultimate strength, SU. That is ultimate strength. Does it make sense? And this is where we find, so there's more to it, like it says for building light structures, design stress, American Institute of Steel Construction, design stress, yield strength divided by, so this will be a design factor. You can see it's less than 2, 1.67. If you work with aluminum, 1.65, but these building light structures assume, one-time loading. That's the dead load, and then occupants, their additional load is assumed negligible. Bridges is different. For bridges is again, this is meant the class or civil engineering majors. You'll learn more in the structural class. Okay, general machining. So not Y and U. I know this table, and these tables are repeated in the text in the chapter, and here in the chapter it says SY. Let's use SU. Okay, so table 3.2 in the chapter has this as Y. Let's use U. And then it shows, so again, appendix 17, we'll go to it over and over. It tells to pick the proper design factor, and also tells us how you can, approximate ultimate strength in shear when you know ultimate strength. Ultimate strength and shear, or ultimate strength. Again, these are approximation. They should be the waved equal sign. And then there's this other equation. So design stress and shear, like we did the last part for the problem on board, and yield strength and shear. And you can see yield strength and shear approximate is 0.5 of yield strength in tension. Okay. Or you move this below, so you divide by 2. And for ductile material, there's a better approximation that goes 1 over square root of 3, which is 0.577. So sometimes we're going to use that other approximation. Well, not in this class, but so yield strength in shear being 0.577 times yield strength in tension. Okay?
Question for the design factor, is that pretty much the industry standard across the board for civil engineering, or is that calculated?
Yeah, there's code. I mean, here, American Institute of Steel Construction, and depends on the industry. Aerospace industry, because they want to design lightweight. Again, what we're going to discuss is why have a design factor. So why don't go at the limit? Like 2, you can double the load and only start to yield the material. So why do you do this? To capture uncertainties in the loading, to capture uncertainties in the material, to capture the approximation that you make when you model you make a perfect model. You assume loading to be all axial and nicely placed and stuff like that. And then you can see repeated loads and shock and impact. The design factors increased. And then you relate to, if we go back to the top of the table, we relate to other properties, the ultimate strength. So repeated loads, ultimate strength, impact or shock, ultimate load. In design and machine elements, which follows after you may take it in fall with me, we're going to learn how to more accurately evaluate design factor when we have repeated loading. That's fatigue. You know, everybody talks about that Titan submersible that imploded. The problem was, well, I don't know, maybe you read how they studied haven't publicized yet how they looked. I watched a YouTube, somebody said it, composite part delaminated, so as it got squished, it started delaminated from the inside, but that's composite, it's not like a steel or aluminum that we know more of it. So they went in on uncharted ground and they did, I think that was the first they built and they kept on diving with it, right? They did 15 dives so far. 15 dives, okay, but there were passengers that said that they could hear cracking sound, and that was of the delamination that was happening. Composites are unpredictable, and they are not following any rules. Boeing that apparently supplied them was the pre-pregs and was aged, was expired. They didn't want to use it. They declare decline any responsibility, but you know, there are composites used in airplanes. But they have the means to verify. They do ultrasound to check for voids and cracks, and they, you know, I express some skepticism. So, but they you know, they know what they are doing. There's a full industry, not some small business that wants to make money taking people under the water. So they do ultrasound testing in areas that know are stressed, and they're probably going to replace the part if possible, or just, you know, declare this is the life of the airplane. Do you know anybody that flies the plane? I know somebody, well, was a student in class and we talked a little bit. So when you buy a used plane, you ask how many hours? It's what you ask. And they said 2,000 hours, and the frame is guaranteed maybe 5,000 hours or 4,000 hours. So you know you have this much life left. Aluminum does not have what is called infinite fatigue life. So airplane frames, they know how, it might be more than that. I think they fly in the neighborhood of 30,000 hours. Usually it's the takeoff and landing cycle, and then for the body, you know, the pressurized, because it's pressurized and outside is low pressure, and then coming back to equal loading. Anyway, so for aluminum, because it has been used for quite some time in the aerospace industry, they know things more, and they know, okay, this frame will, you know, you fly only 10,000 hours, and then you scrap. You know, things happen. Like was a Japanese internal flights, and they did a repair to it took off once, and they touched the tail on the runway, and they did some repair, and on one flight it lost the tail section, and the plane crashed. Almost everybody died. I think there were 1 or 2 survivors. So, and that was judged as improper repair. Okay, with the composites, they don't have that experience, primarily working the other way, to where it's pressure on this outside and want to collapse it towards the inside. So, you know, I mean, they signed, you know, the waiver. The company is not liable for their death, and they even pay money to go underwater. Anyway, so why design factor? I enumerated a number of reasons. The difficult to capture is the repeated loading. And we have some knowledge for some of the material like steel, aluminum, titanium, steel alloys. You know, if you have repeated loading applied, steel has the property at certain stress level that can last forever. Aluminum builds up fatigue even of low stress level. So that's why aluminum, it's known not to have an infinite fatigue life. So aluminum frames, for classical frames of aircraft, they have a limited life as a rule. Anyway, so 1 and 12. Let's do some other problems, and then we'll begin the next chapter to discuss, you know, more along this line. But yeah, the short answer is yes. There is experience. Design factors are based on experience. I mentioned. I just opened to, you know, a stress strain curve for a ductile material. Aerospace industry, because they want to save on weight, they go with design factors that you don't find them in general machine design. But what they do instead, they have periodic checks, and they also have more stringent requirements upon the properties of the material. So a batch of, say, aluminum sections for the wings, they want to know the certificate for that batch. What is the yield strength? What is the ultimate strength? And to reduce the uncertainty about the material's properties, because you can buy a batch of ordinary steel, structural steel. You buy it on a Friday, or you buy it on a Tuesday, and so it all depends. It might be a good, maybe they repeat this. Students went to visit Steel Dynamics over in Sinton. There's a Steel Dynamics, a mini mill, a big company, but they have a mini mill here in our area. And we discussed including so they have orders for, they do primarily thick plates and rolled steel for automotive, and they form it in structural shapes. But they do testing. They test, they cut specimen, they have tensile machines, and they attach bulletins to the batch. And if the batch does not match the requirement for one customer, they go with the next one. They use as a primer recycled steel. They do some sorting, of course, but based on how well they recycle and how that batch worked, it may or may not be within the acceptable limits for one customer. So they keep it for less demanding. They sell it more, maybe for less, and then they go to the next one that they can certify. They cut specimens from the middle, from the two ends, and if it's within the acceptable limits, they give it they ship it. Okay, goes well with the manufacturing process class. Here's a place where knowledge of dynamics, although they give the force, centrifugal force, directly, but we can calculate it, can we? You had dynamics. Everybody had dynamics? I don't think it's required for this class. Strength that is required for this class. So where's this coming from? The centrifugal force is going to be the radius of the centrifuge. This is the center mass of the basket. It hinges at the end of the arm. The arm rotates about a point here in the horizontal plane. Let's not forget there's weight that's adding to it, right? So we have, maybe I should take a screenshot and go back here, select all, paste, and okay, so let me raise this. Oh, for reality, I need to clean the board, and I need to lower the figure. So the centrifuge arm rotates about vertical axis in the horizontal plane. The force that loads the pin in double shear is going to be the resultant of the weight of the weight of the basket and the centrifugal force. And you can calculate the centrifugal force by knowing that is mass times the centripetal acceleration. So do you remember the centripetal acceleration? If you have a body that moves on a circular path, we have velocity v. So there will be what? Omega. So what is the centripetal force? Well, we have centripetal force, the one that keeps it on the path. That could be, if it's in a car running in a circle, it will be the friction between the road and the tires. So this is centrifugal force, and this mass times centripetal acceleration. Okay, and centripetal acceleration, or to use capital R, is going to be so m times r omega squared. You remember this? And you can also write it in terms of v. So v is going to be R times omega. So you can say mass times V squared over R. You know. So sometimes, yes, the force analysis may require additional, or it might be more involved. Not necessarily here. Okay, so the book tells us like F centrifugal force is mass, and then they have some coefficient. So if we're going with this equation, you have mass times R, and then instead of omega, they get the RPM N. So what is the relationship between RPM and omega? So we have RPM N is going to be 2 pi. Actually, no, the other way. So I have omega is 2 pi times N over 60. Omega is radians per second. Is that correct? So every turn I do 2 pi radians. I have n turns per minute. These will be in radians per second. This is rotations per minute. That's why I divide by 60. Or you can say pi over 30 times n. I'm sorry. So they say it's m, or we can write m times r times would be omega squared, so it'll be pi squared times n squared over 30 squared. Well, if you take pi squared divided by 30 squared, you'll get that 0.091, whatever they have there. 0.01097. You can verify. Everything else is like we did it for the problem, you know, when with the addition, what I added to the previous problem. So just take the centrifugal force, divide by 2, no diameter of the pin accidentally is 10 millimeters, or coincidentally. I started saying so we have the centrifuge arm with the hinge and the basket, and you have the weight, and you have the centrifugal force, M times G. So really what's, and the basket aligns itself with the resultant, by the way, mg. So this resultant is just going to be the force that's given in the text of the problem. So it would be mg squared plus fc squared square rooted, to be more rigorous. Does it make sense? They indicated as a load force only the centrifugal force, but assuming the arm operates in the horizontal plane, there's also the weight that's going to be less and less significant as I increase the RPM. I think they have it in Houston and elsewhere where they train astronauts and pilots. They put them on, poor people, they put them in centrifuges. They have they hold in their hand and they press a button, and when they faint, they just let the button go and they stop. But this is how they train. They put them on a centrifuge. Why is that? At launch, as the rocket moves up, it accelerates quite a bit. It can be 3-4 times the acceleration due to gravity. Maybe you've seen movies where they are all in their, they launch them laid flat, perpendicular to the direction of acceleration. And when the first rocket stops firing, they just, have you watched those early Apollo mission movies? Why is that? Because they no longer accelerate, so they run, or inertia moves them forward. Again, I'm not going to go through this. Let's do another problem, or let's do a problem on frames. It's something you did in strengths of materials. Okay, so frames, this could be considered a frame, and but let's look at this one. Okay, So I'm taking yet again this screenshot, select all, paste, and then cut, select all, paste. All right, so have you seen this kind of problem in statics? All right, so we're assuming that these structural pieces are pin jointed, and loads are applied at the nodes. It's what we do, and we can solve it. Firstly, it has to be statically determined. So this is a pinned end, and this is a sliding point. You see them as a rule to account for any thermal expansions. There are bridges. Harbor Bridge. I took a picture of the rollers. I could show it to you, could project it. So in order to allow for thermal expansion, these ends are not fixed, but are put on rollers to allow for a length increase. So you need to figure out the reaction force of the supports, and then you can use the method of joints, or you can use the method of sections. With the method of joints, you can, because you use just a sum of forces, you can solve for, at the time, only for two unknowns. With the method of sections, because you can write moment equation, you can solve for three unknowns. All right? So, let's see. Can I make this a little bit smaller? I think I could. So, would it be? Select all, resize. Oh, too small. Undo, select all, resize, and maybe 75. We needed to, what the problem requires us to do is to calculate the loads per each. I'm sorry, I'm just going to stay with what I have. So to calculate the stresses on each of the links, we're going to do just one or two of them, and then apply both the method of sections and the method the joints, and then the method of sections. So firstly, I need the reactions at the supports. Again, this is assumed to be sliding pin. This is a fixed pin. And we have two loads. I can do a free body diagram of just the entire frame. Okay, so force and force. One is 600 pounds. One is 1,200 pounds. And then I have reaction at A, and I have reaction at F. Is there going to be the pin can also take a horizontal force reaction? So this is, I could say, vertical reaction at A, horizontal. But I know from the beginning that the reaction at A in the horizontal direction is 0. Why? Why is it 0? Because these forces, I don't have a force that has a horizontal component. So I just take this, from the beginning, I know it's 0. Okay, but definitely this one does not take horizontal force because of the sliding, the rolls. So I need to calculate the reactions at the supports. So I need to take 6, 6, 6. Okay, and we sum moments about, this is A, this is F, this is B and C. So we sum moments about A, and we have equilibrium, again, positive counterclockwise. So what do we write? We write negative 600 times 6 feet, and then negative 1,200 times 6 + 6, 12 feet, positive RF, which we don't know, this is the unknowness equation, times the full length, 18 feet, equals 0. So RF is going to be, I move everything to the other side, it becomes positive, so it'll be 600 times 6 plus 1200 times 12 over 18. And you're going to see this over and over and over and over as we do bending, beam bending, calculating the reactions of the supports. You have them wrong, the entire problem is wrong, of course, because it relies on, for stress analysis. The bad part of lecturing 2 hours in a row. Okay, so let's calculate this. It'll be 600 times 6 plus 1200 times 12 equals, oh, you're right. Thank you. Students don't do that. Let's see what he does. Okay, he will mess it up. All right, so 6,000 in the plus the small one. All right. Actually, you know what I can do? I can pull a 1,000 in front, and I can say 6 times 6 plus 12 times 12 over 18. What about this? So 36 plus 12 squared, 144 over 18. Wow, so nice. 10 times, so this is 10,000 pounds, okay? And we can put it on the drawing. This was RF, 10,000 pounds. And then we need to, you may be tempted to go and say, okay, some force in the y direction, calculate RA. Let's hold it for verification. So we're repeating this moment equation. So sum of moments about F equals 0. Likewise, counterclockwise positive. So what do we have? We have RA, the unknown in this equation, times 18. And that will be a negative. And then I have positive 6,000, I said, times 12. And then I have likewise positive, my choice of positive for moments. So positive 12,000 times 6 equals 0. So I have RA is going to be, well, I can write again like 1,000 in front. So 6 times 12 plus 12 times 6 over 18. So 6 times 12 plus 12 times 6 equals over 18 equals. So that's 8,000. Okay, so I put it here, RA 8,000. And only now, so I'm going to sum forces in the y direction or vertical direction and see if it's indeed 0. So we'll see what? We're assuming positive up. So we have 8,000 and then negative 6,000 and then negative 12,000 and then positive 10,000. Is this indeed 0? So let's say 8, I can even say 8 minus 6 minus 12 and then plus. This was supposed to be plus. So 8 minus 6 minus 12 plus 10 equals 0. We've got it. So we can now invest in, doing further analysis because we have a certainty that the known are, reactions are correctly calculated. So let me show them, at some point we're going to erase this. So let me show them directly on this original figure. So again, this is 8,000 pounds, and this is 10,000 pounds. Okay? With the method of joints, I said we can handle 2 unknowns at a time. So we need to progress with the analysis such that as we move forward, we have only 2 unknowns that we're dealing with. Okay, and we are making the assumption that all links are in tension, although some may not be in tension. So I'm going to take this piece. Let's see, I'm in Paint and I can do this. So I use the brush tool or the eraser tool, and so I make a break here, and I make a break here. Imagine like being what? Being removed, not necessarily or not shortened, but rather, you understand what I'm doing? Okay. And then I have likewise here. Okay. So this is the method of joints, and I isolated one joint here, and I'm going to, again, I said that the link is in tension. So the link in tension means that it's loaded with forces like so. Is it clear? Do you follow? And then I have the other force, because they are like internal forces. When I put in place, this and this externally cancel each other's effect. Internally, they stress the links. And I'm assuming, like I said, all of them to be in tension. It means that, okay, so it means that a link in tension causes a force at the node that is away from the node. Okay, so I have what? I have FAB here, and I have this one. Well, I can write it because it's common to the two, FAB, and I have FAD. All right, and likewise, it's FAD here, and likewise, these are two force member. We neglect the weight of the link itself, although it might not be negligible. But that's what we do. So this is FAB likewise. Okay. So if you look at node A, we have two unknown forces, that is FAD and FAB. This is a known force. If I go elsewhere, like at this node, for example, before taking care of this, so this will be an unknown, and I have an unknown here, here, and here, too many, 3. So I cannot deal with this one. I can go tackle either this one or this one first. Will be the same story. Well, yes and no. I mean, this and this are not equal. If they were equal, then due to symmetry, I'll see the same, whatever. Anyway, so yeah, we can take care of node A. I'm going to erase this and just sum forces in the right equilibrium for forces in the horizontal vertical direction, and we can solve for the force that is loading link AB. So we can calculate the stress in link AB, sigma in the link AB, as being FAB divided by area of AB. And here it says AB is a C3 by 4.1, and it's doubled. So 2 C channels back to back, like a fabricated I-beam, made of 2 C channels. You weld 2 C channels, and it gets you a fabricated I-beam. So you can look up at the back of the appendix what's the cross-sectional area of 1 multiplied by 2, and we can calculate the area of AB. Well, let's take care of the force itself. So I said we write sum of forces at A, sum of forces in the x or horizontal direction equals 0. Sum of forces in the vertical direction equals 0, again at A. So what do we have? In the horizontal direction, I have FAD positive, which is an unknown. And then I have likewise positive with the assumed, we may end up this link being actually in compression if we get an FAB that is negative sign. So it's going to be FAB times this angle here. So let's see what this angle equals to. I have 6 feet and I have 8 feet, right? So, and then what is the AB length? Is it 5? So AB is going to be square root of 8 squared plus 6 squared. This is equal to, so 8 squared plus 6 squared equals square root. That's 10. So these are Pythagorean numbers. This is 10 feet. Okay. We can calculate the angle directly, or we can just say sine of this alpha, sine of alpha is just going to be 8 over 10, and cosine alpha is going to be the other one, 6 over 10. Okay, so let's continue here. We have FAB times cosine alpha, the other unknown, times cosine alpha. All right, and this is it. In the vertical direction, we say positive is up. So we have 8,000, and then I have the vertical projection of FAB. It's also positive, positive. FAB sine of alpha. And then, so 1, yeah, this was it. So equals 0. I don't think we missed any component. I need to step away for just a little bit. So vertical 1, 1, horizontal 1, 1. Okay. Again, cosine alpha is 6 over 10. Sine alpha is 8 over 10. So we have two equations, two unknowns. The second one has just one unknown, so you can solve for FAB from the second one. FAB is going to be negative 8,000 over 8 over 10. So 80,000. So I have really 1, and how many zeros? 1, 2, 3, 4. 1, 2, 3, 4, 0. That is 10,000 pounds. Okay, and with this one, I can go back to the first equation, and I can say FAD now. It's going to be this, move it to the side, so it's going to be FAB times 6 over 10, which is, oh, I forgot the minus. Minus is important. So and we need to use it with its sign. So it's going to be negative 10,000 times 6 over 10. So this makes for negative 6,000 pounds. Was it clear? Okay, so we've got FAD negative 6,000. And we've got this one, negative 10,000. Which means that both link AB and AD are actually in compression, not in tension. Okay? Is it really? Positive. Positive, yes. So I've got this negative 10,000. Yeah, apparently. So they are both in compression. And then, you know, once they have this and this, actually, the next step would be, of course, we can start from, move to this other one. It has the same level of advancement into solving a problem as the point of A. I can move to this point D, and I have FAD now. There will be unknown force BD, unknown force DA. And once I have this one, then I'm left with two unknowns. I can move to point D, to node B. Was it clear? We could calculate the stress. So it was FAB. There will be a compressive stress. So negative compressive. So 10,000 and divided by area of AB. And for that, we need to go to the back of the book. So again, is C3 by 4.1, pretty lightweight. So appendix and C channels, let's find them quickly. Okay, there we have C channels, and let's rotate the view. So what was it for? Like the last one, T, okay? So it says area, area in inch square is 1.21 square inch. This one here. So C, well, was here before. So the area, so will be 2 times, I'm looking at this number, 1.21 square inch, and calculate the compressive stress. So let's move back to paint. And so that stress there is going to be a compressive stress, and it's 10,000, 1, 2, 3, over 2 over 1.21 square inch, and it's 4,132, negative 4,132 PSI, pound per square inch. Again, it's compressive stress. You may have to, if it's compressive stress, you may have to run a buckling analysis for those links. Okay. All right. So that's for one of the and I said next would be this one, and then I can move to this here, and so solving for 1, 2, and then if I have these 2 known, I can move to this one. And then I know this, 2 unknowns, and maybe use this for verification, to where, going from left to right, I end up with F and see if I get correct equilibrium equation for the last node. Let's go back. So was it clear? Again, this is something you've done in statics. Have you practiced method, which one mostly? The method of section or the method of nodes? Don't remember. You did both. Okay. The little extra was this part really, where we calculate a stress. Let me erase this, and let's do the method of sections. Like I said, with the method of sections, you can solve for 3 unknowns at a time, because you can write, in addition, moment equilibrium equation. So that allows you for 1 additional unknown to be handled. I need to stick this far up. A little bit of, come on. All right, select all, and I move them a little bit to this. All right, so I take the eraser tool. Let's see where we could do. I mean, if we do a section here, we do the method of nodes. We can do a section all the way, and we introduce 1, 2, 3 unknowns, and we can write equilibrium of this, what's left of this. Okay, so, or the right side of the frame. So I can take this tool actually and delete this. Again, if it's away from the node, we have, and it's confirmed positive, it means that that link that was removed is in tension. If it's towards the node, it means that, or rather the sign ends up being negative, it means that that link is actually in compression. So we have this is force F, rather BC. This is the force BE, FBE. And this is the force DE. Okay? And we know this. This was 6,000. I think it was 6,000. 6,000 pounds. Okay. Again, well, I can even erase this. You know, I can totally delete the right-hand side. So we can state equilibrium, all three equilibrium equations for the left-hand side of the frame. And so let's see what we have. We can sum moments in a convenient way about, at least at the first glance, about point B, and that will eliminate the two unknowns from the equation, and we can solve for this one right away. So I'm going to say sum of moments about point B equals 0. Again, assume positive counterclockwise, and let's see what it translates into. So it's going to be the FDE, it causes, as shown, it causes a positive moment. So it's going to be FDE, which is an unknown, FDE. And what's the arm of it? It's 8 feet times 8. And then I have the moment, again, I'm about B, the moment of the 6,000, or reaction at A, support A, which causes a negative moment, and that has an arm of 6. So negative 6,000 times 6 equals 0. So we can solve for FD. And FD, it gets up positive, so it means that this is in tension, D is in tension. So it's going to be 6,000 times 6 over 8. We can calculate. And then we can write, sum of forces in the x and y direction. So I can say sum of forces in the horizontal direction equals 0, horizontal being positive this way. And we have what? We have FDE. And then we have FBC, positive, plus FBC. And then we have the horizontal component of FB. So, and that will be also positive FBE times cosine of an angle here. Let's call this beta. So times, it's a cosine. Actually, no, it's sine. Times sine of angle beta equals 0. Do we have anything else in the horizontal direction? This one, the horizontal component of this, and this one equals 0. So let's see what sine of beta is. We have a triangle, or yes, and this distance BE is going to be, we've got it before, so it's 10. So we sine of beta now is going, so sine of beta is going to be 6 over 10. Cosine beta is going to be 8 over 10. All right, so we can replace this with, we said 6 over 10. Let's take care of this. We can put a number on it. So 36 over 8 times 1,000. That's 4,500, 4,500 pounds. And this one goes here. It's premature to solve for any of the remaining unknowns, so you need to state sum of forces, equilibrium equation in the vertical direction was positive up. Okay, so what do we write here? We write, we go from bottom up, so we have positive 6,000. And then we have, as we move up, we have a negative FDE. And that's times cosine of beta times 8 over 10. And then I have a is it positive? No, it's a negative 6,000, the original or the external load, equals 0. Okay. So these two are by them, or yeah, can be solved now. We have two equations to unknown. we can solve for FB from the second one. So FBE is going to be, move this to the right, but flip the equation. So it's going to be 6. Actually, I can tell right away what the value is. Can I? This plus this is 0. So this FB is 0. FB is 0. Nice. So we move with it. We move up. And we can solve for FBC. So, or rather, so FBC is going to be, well, again, this is 0. So FBC is going to be negative FD. So FBC is going to be negative 4,500 pounds, meaning that this one is in compression. So in actuality, we assume tension, but it's actually in compression. So we can calculate the stress. There's no stress in FDE. We can calculate the stress in link BC. So sigma BC is going to be a compressive stress. We saw compressive stress elsewhere, and it's going to be 4,500 over, so what is BC? We look here, BC, the same. So will be 2 times, what was it, 1 to 1? I don't remember from, yeah, 1 to 1. Yeah, it happened that these two link BCs fabricated of 2 back-to-back C channels, and we can calculate the stress. Again, it's compressive. And so 4,500 over 2 over 1.21. So this is negative 1859.5 psi. Okay. Again, when you have compression, buckling it might be of, consideration. So verify for buckling not to occur. And what else we could do? We could, we can solve for using the same approach for this other half. And so let's see, we have 1, 2, 3 unknown. We can ignore the findings so far and verify the correctness of the results. It's silly not to use any opportunity to check your approach, your calculation. So we can state the equilibrium equations for the second half of the frame. It's symmetric, yes, but we have different load here. Let's see. Really, if you look at the problem from behind, so if this were on glass and I'm on the other side of the glass, I see this problem with different, so this was 6,000. I need new markers. And this was what, 10,000? 10,000 pounds, okay? So, but yeah, if you have something that you've done wrong, I mean, you carry that mistake with you. However, to expedite calculations, you can just, look back at these equations and where was the reaction force of 6,000? You put 10,000, and when was 6,000 vertical load, you put 12,000, and you get the answers. But otherwise, working independently with that change, the mirror figure, you might be able to run into a mistake. I do coding, I write code, computer code, and sometimes there's a mistake, I cannot find it. So what I'm doing, I'm starting changing names maybe as I'm doing it. Like you clean the house, you lost something in the house, but you do a cleaning, maybe you'll find the lost item as you do the cleaning. Or invite somebody. That's an excuse to clean the house. Anyway, so this was the most we could do in 2 hours. It's 1:57. I can turn this off. Yeah, I deleted everything on my cell phone, so I hope the microphone won't work.